Hello. So, welcome to another session of physics. So, today we'll be discussing a problem on rotational dynamics. So, let's see. So, I'm pasting the question over here. Okay, so I believe that the question is visible. Oops, let me just show it. There you go. Okay, so in today's session, we'll be talking about rotational dynamics. Rotational dynamics. And I will explain the concepts as we go along the problem. Okay. Now let's just look at the problem. Here we have a wrecking ball, which weighs about 4,800 newtons, is supported by a boom, which may be assumed to be uniform. Okay, that's good. And has a weight of 3,600 newtons. Okay. As the drawing shows, okay, a support cable runs from the top of the boom to the tractor. The angle between the support cable and the horizontal is 32 degrees, and the angle between the boom and the horizontal is 48 degrees, okay? And find A, the tension in the support cable, and B, the magnitude of the force exerted on the lower end of the boom by the hinge at the point B. Okay, the magnitude of the force exerted on the lower end of the boom. Okay, so we need to find out, first of all, the tension, of course, the tension which is acting on this cable, and the force acting at point B. All right, now here, so once we study dynamics, so in dynamics we're discussing the forces, right? The forces which cause this object to accelerate and all this kind of stuff. So there are two cases of dynamics, the linear dynamics and rotational dynamics. So once we study rotational dynamics, we incorporate the linear dynamics in this as well. So here we have a problem, and here we have this subject, or rather, we have this subject. So we have a boom, right? We're trying to find out all the forces acting on the boom. Okay. So first of all, we look at the free body diagram. So see, this is our boom over here. Just gonna draw a rough figure, and there we are. Now what we're gonna do is we are gonna look at all the forces acting on the boom. All right. Now, what are the forces acting on the boom? So obviously there is this wrecking ball, which is connected by the cable over here. So the wrecking ball's weight will be acting straight down. Right. So that is what? The gravity of the wrecking ball, which is given here. Thank God, it's given here. How much is it? 4,800 newtons. So we'll just call it weight of the wrecking ball. There you go. Weight of the ball. All right. Now, what else is acting on it? There's a tension. Yes. Which way is the tension acting? The tension is acting this way, around that way. Okay. And an angle is given 32 degrees. Okay, we'll get that. So this is our tension T. What else is there? There is the weight of the boom itself, right? Because, of course, the boom has weight, and that weight is going straight down. We'll call that weight of the boom. Oops, I've written weight of the wrecking ball over here. So let's just call it W, a big B, a capital B. All right. And then we have our hinge forces, which is acting at this point P. Right. Now, hinge forces, for example, if this is our wall and I have let's say, a rod which is fixed on this wall here. Now, obviously, there is gravity which is going down. Now, when you look at it, there is nothing to support the object. So the object, the boom, the beam over here, is in equilibrium, which means that the net force acting on the beam should be equal to zero, right? So I'm taking this lesson with the understanding that you know the basic principles of forces and stuff. If not, it's okay. We can just go over the concept as we go through the problem. So here, this object is at rest, which means that the net force acting on it is zero, which means that see, there is only one vertical force going down. So in order to balance that, there should be a force going up, and that is provided by the hinge force, the vertical hinge force over here. Okay, so that means that here, wait, let me just get rid of this. Okay, so here there will be a hinge force which is going both vertical, we'll call it the vertical hinge force, and horizontal. Okay, obviously there's going to be, because see, if again we come to the case of the wall, let's say this is our beam, and here gravity is pointing down. Okay, uh, second, gravity is pointing now. Let's say I use a wire to help hold the beam in place. So gravity is going down, tension is going this way. Again, the beam is at rest. or rather, the net force acting as zero. So the net force in the x and y have to be equal to zero, which means that there will be a vertical force which is going up to balance gravity, which is V, and a horizontal force going this way to balance the tension. Okay. Now, so these are all the forces which is acting on the boom. All right, now what do we do from here? Here we have the angles too. Okay, that's good. Now we need to find out the tension force. So the first thing that we will do is we know that the object is at rest, right? The object is stationary. The object is stationary. We call that linear equilibrium. Okay, this is translational equilibrium. The object is in translational equilibrium. Now, what does that mean? Translational equilibrium just means that the net force acting on the object is equal to zero. Now, here, since the forces are acting in a plane, the net force acting in the x direction as well as the net force acting in the y direction have to be equal to zero. Okay. Now let's see. So we have all one, two, three, four forces acting in either x or y directions, but the tension is not acting in either. So what we do is we split our tension into x and y components. So this will be the x component of tension, and there will be a component of tension which is going down like this, Ty. Okay, this is Ty and Tx. Right. Okay, now we can just write down our equation. So how would that look like? Let's see. So we have T, okay, so let's see. So we have two forces going in the horizontal direction. So I can write net force acting in the x direction is equal to zero, which implies that Tx should be equal to the horizontal force. Right, because the net force, the sum of all the forces acting in the horizontal direction, must be equal to zero. So you have the tension going left, the x component of tension going left, and you have the horizontal hinge force going right. So they have to balance each other out. Now, this is our first equation. Now, the net force acting in the y should also be equal to zero. So what do we have over here? And the y is equal to zero, which means that here there is how many y forces are there? Okay, there is the vertical hinge force going up and two weights going down. Right. So also the tension is going down, three. So the vertical component, which is going up, should be equal to all the forces going down. That is the y component of tension plus the weight of the boom plus the weight of the wrecking ball. Okay, this is our equation number two. All right, so we have an idea. So from here, how many forces do we know? We do not know the tension, right? We do not know the horizontal or the vertical forces, hinge forces. We do know the weights, however, right? Okay, that's good. And we know the angles too. So we can easily see what we can do here is, what I can do here is I can just say that the tension x component, okay, let's see. So we have the angle 48. So this angle is equal to 48. This angle here is equal to 48, okay? And this angle here is equal to this tension going here. This angle here is equal to 32 degrees. Okay, so if this is 48, this entire thing becomes 48, right? This entire thing is 48 degrees, okay. Now we need to split tension into its x and y components. So we have to find out. So here we have to find out what this angle is. And if you look at it closely, that angle will be 32. Why? Let me just explain that. Let's see. This is our scenario where this angle is equal to 48 degrees, right? And you have the tension force going this way. There is a tension force, right? And we know that this angle is equal to 32, right? So hear me out. So this angle will also be equal to 32. Right. Now this is our tension. Now we can split tension into its components. So here, this was our Tx. Remember, this was a horizontal component of tension, and this was a vertical component of tension, Ty. So I can say that the horizontal component of tension is equal to T cos 32. Okay, and my vertical component of tension, Ty, is equal to T sine 32. There you go. So you have the components. Now I can just plug them over here, right? I can just plug those things over here. So let's see. I can just plug these values over here to make the equation a little bit more better. Should I do that now? Yeah, I mean, we can just do that. So this will be T cos 32 is equal to the horizontal force. Okay, you know what? I can just write it like this. The horizontal force is equal to T cos 32. The vertical force is equal to T sine 32 plus the weight of the wrecking ball. How much is that? The weight of the wrecking ball is 4,800 plus the weight of the boom. So that will be 4,800 plus 3,600. So here, I'm going to write this is 4,800 plus 3,600. So how much will that be? That is 5,100, right? So you have vertical force is equal to T sine 32 plus 5,100. There you go. So this is our first equation. This is our second equation. These are the equations that we got, okay, while solving for the translational equilibrium. Okay, it's very important. It's translational equilibrium. It's not the total equilibrium. This is a translational equilibrium where the net forces acting on the object is equal to zero. Okay. Now we will move on to the rotational equilibrium. So we've established that the object is stationary, right? The object is not moving, nothing is moving. So it has to be the net forces acting on the object has to be equal to zero. They have to balance each other out. Also, the net torque acting on the object or the system have to be equal to zero. Because if the net torque is not zero, then the object will inevitably rotate. Right. See, for example, if this is my, let's say, seesaw, okay, and if a kid is sitting here, okay, that's a very bad representation, but yeah. So let's say a kid is sitting here. Now, the seesaw is not balanced, right? The force of gravity due to the kid will create a torque on the system, right? Create a torque on the system, which will cause the seesaw to rotate, or rather, it will cause the seesaw to accelerate. That is rotational acceleration. Okay, so here, so if I need to balance this, I need to keep something else over here, right? Something else over here. It doesn't have to be the exact weight of the kid. The torque should be equal though, right? This will create a counter torque in this way, which will balance the torque created by the kid, such that the net torque acting on the object will be equal to zero. All right. Now let's check the torques acting on the system. Let's see. Net torques acting on the system. Okay, so in order to check the torque acting on the system, we need to find out the axis of rotation. Okay, this is very important. We need to find out the axis in which the object might rotate. Okay, and the good thing is that you are at the liberty to choose the axis. You can just choose the axis wherever you want. But there's a catch. You can choose the axis in such a way that it will make your equations more smoother. Okay? See, for example, if you look at this problem over here, if you look at this problem over here, there's actually another force going up over here. This is called as a normal force, right? Now, suppose I don't know what the normal force is, but I know that, but I want to solve for rotational equilibrium. I choose my axis over here. Well, obviously, everyone is going to choose the axis over here because that's the point of rotation. Right. If I choose my axis over here, the torque acting on that point will be zero. Okay, we have two torques. See, this is the first torque. This is the second torque. If I try to find out the torque acting at this point, that will be equal to zero. Why? Because what is the definition of torque? Torque is equal to RF sine theta, right? Where R, let's suppose this is the point of rotation, and this is the force acting on it. F is the force R is the distance from the point of rotation to where the force is acting, and theta is the angle between the force and this displacement vector. Okay. So if I choose my axis in a strategic way, I can make the R equal to zero such that that torque is equal to zero. Okay. It's more intuitive, you see. It's like you don't have to think much about it. The more you do problems, the more quickly you'll get the grasp of it. So here, again, see here in this figure over here, obviously point P is the axis which we'll be choosing. Why? One thing is that it's more of an obvious guess. Point P is where the axis is going to be. The object is going to rotate like this, obviously. The other thing to notice is that there are two forces acting at point P, which is V and H, right? Which are the hinge forces. But we do not know the what do you call it? We do not know either of those forces. So if I take my axis over there, the torque produced by the hinge forces will be equal to zero. Will be equal to zero. The torque caused by the hinge forces will be equal to zero. And that makes our life much easier. So let's see. Can I write it over here? I mean, yeah, I can. Right. Okay. So now we look at the torques acting on the system. So we know that the object is not rotating, right? Which means that the net torque is equal to zero. Okay, you know what? I'm going to write it over here down below. Okay. So the torques. So the net torque is equal to zero. So I can just write sigma tau is equal to zero. Okay, this should be pronounced tau, and it's written like this, although no one actually does. Many people write it as T, but that's okay, as long as you understand what's happening. So net torque is equal to zero. So let's see, what are the forces which will cause the torque? So let me just go back to my diagram over here, and let me just copy the diagram. Okay, there we are. Okay, so here we are. This was our diagram. Okay, now we want to find out the net torques acting on the system. So let's see. So the good thing about torque is that we do not have to split the forces, right? So here what we did was we split the tension. So we're not going to do that. So we have our rod. This is our boom. And we have the weight of the boom going down, the weight of the wrecking ball going down. And we had this angle. This is the weight of the wrecking ball going down. And we had this angle to be 48 degrees, right? We should not forget the angles. And then there was a tension, right? There was a tension force which was going this way, right? Whichever way that is. So, let me just get off this now. Yeah. So let's say it was going this way, and we knew that this angle was equal to 32 degrees, right? This was our question, right? See, now I'm placing my point of rotation over here, okay? This is my point of rotation. I'm going to write it over here. Point of rotation or axis, okay, which means that I do not have to look at the forces caused by the torques caused by the vertical and the horizontal force, right? Because they do not produce any torque as long as my axis is at the point P. Okay, good. Now, this was our tension. Okay, now let's find out the torque acting on the system. Net torques acting on the system. So here, see, this is 32, which makes, let's see, this entire angle was 48, right? And we have this angle is equal to 32. This angle is equal to 32. So this will be 48 minus 32. Confusions? See, this was 48. This was 48. And this was the tension force. Okay. This was the tension force. Oh, God. Yeah, that was a tension force. And this is 32. So this entire thing, okay, so there you go. Yeah. So this entire thing is 48, right? That entire thing is 48. And this is 32, which makes this angle 48 minus 32. Right. I hope there's no confusions in that. So this will be 16 degrees. Okay. Okay. So if that is 16 degrees, see, we have, let me just get rid of this and this and this. So we have this angle to be 16 degrees. Okay, now let's look at the torques acting on the system. So there's only three forces acting which causes a torque. The first torque is produced by the first torque. The first torque is produced by, let's say, the weight of the boom. So that is RF sine theta. This is the equation. What is the R? R is the distance from the axis of rotation to where the force is acting, which will be this thing over here. Right. Now, we are not given any length of the boom. Let me just check. Yep, there is no length. So what we can do is we can just assign a variable to that. We'll just call it L. Okay. The entire thing is L, so this becomes L over 2. See, the entire length of the boom, we'll call it L, so that will be L over 2. So here we have the first torque is equal to L over 2. What is the F? F is the WB. Right, WB sine theta. Now, what is the theta? Theta is the angle between the R and F. So here our R is L over 2, F is WB, so this is the angle. Right. Now, sine of that. Now, what will that be? So we can just consider this triangle over here. So that'll be 90 minus 48. How much was that? 90 minus 48, that is equal to 42. So this will be 42. No confusions. It's very simple. Now, the next torque, torque 2. This is the torque created by This is the torque created by what? This is the torque created by the wrecking ball. So here we have, again, RF sine theta. R sine theta. So R is equal to L, the entirety of the length. F is equal to the weight of the wrecking ball. Sine, same angle. See, this is the L, right? So this will be sine 42 again. Okay. So that's our torque 2. Now the third torque goes by the tension. So that we have torque 3 is equal to, again, R sine theta. We don't have to keep on writing this, but that's okay. R is equal to the entirety of the length, L. What is the force? Force is the tension T, sine of 16 degrees, right? Because see, that's the angle that it makes with the L. So that's our third torque. Okay, now what do? No, we know that the net torque is equal to 0, right? We know that the net torque is equal to 0. Now we need to look at the directions of the torque. See. The torque caused by the wrecking ball is going like this, which will make the beam or boom try to rotate like this. So will the weight of the boom itself. The tension, however, acts the opposite way, right? So the torque caused by the tension is balancing out the torque caused by the boom and the wrecking ball. See, this is torque 1, this is torque 2, this is torque 3. So everything has to be balanced, which means that torque 1, plus torque 2 should be equal to torque 3. I hope there's no confusion in that. Now we just plug in everything together. So let's see, what do we get? That is L over 2 WB. We know WB, right? What is WB? The weight of the wrecking ball. What was the weight of the wrecking ball? 4,800. So that is L over 2, 4,800 sine of 42 degrees plus L 3,600 sine of 42 degrees is equal to torque 3, which is LT sine of 16. Right. Now we can just cancel out the L's because that's why they didn't give us the length in the first place, because we can just easily cancel them out. Right. So we have 4,800 over 2, which is what? Which is 2,400. Sine of 42 is common, so I can take it outside. So I have sine 42 in brackets 2,400 plus 3,600 is equal to T sine 16. Now, from this, we can easily find out what the tension is, right? Because T will be equal to 2400 plus 3600. How much is that? 6000. So that is 6000 sine of 42 divided by sine of 16 is equal to the tension. Should I calculate this? I mean, yeah, I can. So 42 divided by sine of 16 times 6000, that is equal to, so the tension is equal to 14,565 newtons. So we got part A. What was part B? Part B was to find out the vertical and the horizontal hinge forces. That's now cakewalk, right? Because you have the tension now. We go back up. See, we go back up and substitute that in these equations. See, in these equations over here, right? So what do we get? So our horizontal force is just T. What was T? T was 14,565 times cos 32, how much ever newtons, and the vertical force will be 14,565 sine 32 plus 5100, how much ever newtons that is. Okay, so that's it. This is the problem. It's very easy. See how we approach this problem. Let me just tell you how we approach this problem. So this is rotational dynamics, right? We first covered linear dynamics. Okay, we have to have a solid grip of linear dynamics before we enter rotational dynamics. In linear dynamics, we were discussing about the forces acting on the system, right? The forces acting on the system. So see, for example, if this is an object, and this is a horizontal plane, if this is my force F1, this is my force F2, and then I can say that the net force acting on the object will be F1 minus F2, which is equal to ma, Newton's second law, right? But for a rotating system, it gets a little bit more complicated. In a rotating system, yes, we use the forces, but we also use the rotational analog of force, a rotational counterpart of force, which is torque. So here I keep two boxes. Let's say I keep box like this. Now gravity mg will be going like this here. Let's say everything weighs m, so this will be 3 mg going like this. Now we have to look at the r as well. We have to look at the distance. Okay. Now the torque caused by this side will be r1 3 mg. Why didn't I write sine theta? Because see, this angle is equal to 90 degrees and sine 90 is equal to 1. Okay. So if the forces are perpendicular, don't have to worry about the sine theta part. Now here, there's a torque going this way. This will be torque is equal to R2 mg. Right. And if the system is at rest, that means that the net torque is equal to 0. Then these two should be equal to each other. What if it's not equal to 0? What if it's not at rest? That means that the object is accelerating. Object has a rotational acceleration, which again, what we do is Newton's second law, but in rotational form. That becomes I alpha. Okay. So Newton's law in linear form is net force equals ma. In rotational form, it is equal to I alpha. It's the same thing. Why did we use I over here instead of m? Because in linear terms, the only thing which can hinder an object's acceleration was the mass. Actually, the law actually talks about inertia, but in linear dynamics, inertia and mass are roughly the same thing. So we don't have a separate formula for inertia. But in rotational dynamics, mass is not enough. Okay, we need inertia. We need the moment of inertia. Moment of inertia. Okay, and for A is just the angular acceleration. Okay, so I hope that makes sense. It's just a rotational dynamics problem. So we just explain the concept through the problem, and I hope there's no doubts. So I'll see you in the next session. Thank you.